So today I'll be presenting our work on BLAC, that is improving the accuracy of blacklists. This is in joint collaboration with my advisors, Elena Markovic and Milan Yu. IP blacklists contain a list of known malicious IP addresses. Blacklists are commonly used by network operators as an aid to more sophisticated systems like spam filters and intrusion detection systems. Some examples of blacklists include SpamHouse, AlienVault, SnotLabs, or even Project Honeypot. Blacklists could particularly be useful for some networks which are under extremely large volumetric attack or novel attacks that cannot be for which the sophisticated systems do not keep up to. Blacklists are effective in could be potentially effective in such cases because they are very easy to implement. Blacklists only need to check the IP address of the incoming traffic, and if there's a match, they could just drop the traffic. However, blacklists have many problems in them, which make them inefficient. First, blacklists contain fragmented information, because blacklists usually monitor a certain type of an attack and do not care about different types of attacks. Second, blacklist only shows the malicious activities of a particular IP address at a point in time. And finally, blacklists are reactive, because they list an IP address only after a malicious symptom is seen in these IP addresses. So, can we actually aggregate blacklists in a smart way to overcome these problems? Let's deep dive into the individual problems. For the next few slides, I'll be representing the blacklist and the addresses listed in these blacklists in terms of a circle. Now, if a blacklist is effective in capturing an attack, it's represented by a red circle. Now, we see that blacklists may miss many attacks, and this has been shown in previous research. And this is primarily due to the fact that they monitor only a specific type of an attack. For instance, a spam blacklist monitors only spam IP addresses that send spam emails, and probably a malware blacklist lists only IP addresses that host malware. So, compromised machines are constantly being reused and are used to send various types of attack over time. So, an IP address that sends spam email today can send a DDoS attack 3 months later. A possible solution to improve the accuracy of blacklists is to combine multiple blacklists of different attack types so that we can be proactive in capturing the attackers. The second problem with blacklists is that they show only the malicious activities in a snapshot of time. However, some addresses could evade blacklisting by staying dormant for some time and then sending attack again. So, again, to improve the accuracy of blacklists, we could actually aggregate the addresses listed in blacklists which were historically listed to improve the attack detection. However, aggregation of blacklists of different attack types, or even aggregation of blacklists over the past history should be done very carefully because of potential misclassification. Blacklist accuracy varies spatially because of many reasons. One of the primary reasons is that blacklists are maintained by individual users or organizations who pretty much use a proprietary algorithm to determine if an IP address is malicious or not. There can be many errors in these particular algorithms which cause misclassifications. In these examples, the misclassifications are represented by a green circle, where they have falsely identified an IP address to be malicious, but in fact they were legitimate. Now, if we were to combine blacklists of different attack types, we could potentially amplify the total number of misclassifications. Now, to make matters worse, if we were to consider the historical IP address listed in these blacklists, we could amplify the misclassifications even further. So, a potential goal could be to aggregate these blacklists in a smart way such that we improve the accuracy, but also reduce the misclassifications. Finally, the problem with blacklists is that they are reactive, because they only list IP addresses after the IP address has shown a symptom of malicious activities. However, we do know that mismanaged networks tend to harbor more number of malicious IP addresses than networks which are properly managed. So again, a potential solution is that we could expand some of these IP addresses into the /24 prefix so that we can proactively capture these attackers. However, this needs to be done carefully, because if we were to expand all the IP addresses into the /24 prefix, some of the legitimate addresses may be co-located with the same /24 prefix as a malicious address. Therefore, we could again amplify the misclassifications. So the second goal is we have to selectively identify some of the IP addresses to be expanded into their /24 prefix so that we don't cause any misclassification. So here I present BLAG, which stands for blacklist aggregation, and it does it in 3 steps. The first step is that BLAG uses about 157 blacklists of different attack types and combines them into one single blacklist. BLAG then uses a sample of inbound traffic for a particular network and uses a recommendation system to prune the addresses out. Okay, I have no idea why this is happening. Okay. I hope you guys could just follow what I'm saying. So in the last step, BLAG selectively identifies some of the IP addresses and expands them into /24 prefix. Cool. So let's look at the first step of blacklist, which involves aggregation. So we've seen that historical blacklist data could be really useful. However, including all the historical listed blacklist addresses could be potentially causing a lot of problems because they have misclassification. Presta, a related work, showed that recently listed addresses in blacklist tend to be way more malicious than addresses that were listed way back in the past. So we use the same metric that's used by Presta to allocate a relevance score for every address listed in a blacklist. So here is a relevance score formulation, where for every address A listed in blacklist B, we compute it as follows. T is the current time. T out is the last time when an address A was listed in a blacklist B, and L is a constant that ensures that this particular score decays over time. So a high relevance score indicates that a particular address was listed very recently in a blacklist, therefore it's malicious, and a low relevance score indicates that the address was listed way back in the past, therefore it's no longer malicious. Now, the second stage of BLAG is to estimate misclassifications using a recommendation system. Recommendation systems are commonly used by services such as Amazon and Netflix to pretty much recommend new products or movies to users based on their previous histories. This is especially useful for these services because it increases their customer retention and also increases their revenue. Let's look at an example how a recommendation system works. Here, we have 6 users and 6 books who have rated books on a scale of 0 to 1, where 0 is lowly rated and 1 is highly rated. Now, there are several features or factors that influence a particular user to rate a book very high or to rate a book very low. Now, let's take an example. The last user seems to like read books a lot. Therefore, they have given a very high score in their ratings. At the same time, they seem to hate yellow books. So they're given a pretty low score. Now, a service such as Amazon would be very interested in knowing if a particular user, such as the user 1, would be interested in the green book or not. If they are interested, then Amazon would recommend that particular book to the user, hoping that they would purchase it, therefore increasing the revenue. So after running the recommendation system, we see that we get a recommended score or a predicted score of 0.7, indicating that this particular user may actually like the green book. Now let's understand how this number was brought up by the recommendation system. If you look closely, user 1 and user 3 share similar rating patterns because they've rated all the blue books high, ranging from 0.8 to 1. The recommendation system is able to pick up this particular similarity and see that since user 3 has already rated the green book to be 0.6, it gives a very similar score of 0.7 to user 1. BLAG also uses the recommendation system, but to capture misclassification. At first, BLAG arranges the IP addresses in forms of row and all the blacklists in forms of a column. Now, if an IP address is listed in a blacklist, its corresponding relevance score is filled in that cell. Observe that this particular matrix is sparse because not all IP addresses are present in all blacklists. Now, BLAG proceeds to include a new blacklist known as a misclassification blacklist. And this blacklist contains only misclassification. And this is curated for every network by using a sample of the inbound legitimate traffic. Now, in this example, we see that there are 3 IP addresses for this particular network that are legitimate, and therefore BLAG allocates a score of 1 to these IP addresses. The goal of BLAG is to then predict the relevance scores for the other IP addresses that are not present in the misclassification blacklist. Now, here the intuition is that if the recommendation system is able to find similar IP addresses that share features that of the false positives or misclassifications, we could potentially prune those IP addresses out during aggregation. So after running our recommendation system, we see that IP1 and IP2 are kind of similar. This is because they both are listed in blacklist 3 and share similar relevance score. Now, the recommendation system is able to pick this pattern up and allocate a pretty high score for IP1 of 0.75 because IP2 already has a misclassification score of 1, the relevance score of 1. Now, so therefore IP1 is likely to be a misclassification. Now, Black then uses a predefined threshold for every network and is able to prune out the IP addresses that are likely to be misclassified. So why a recommendation system? At any given point in time for a particular network, there's only a small set of legitimate addresses known, because it's impossible to know what IP addresses are legitimate at any given point in time. Also, there are many several factors that influence an IP address to be a misclassification in a blacklist. I've given an example of the proprietary algorithm used by blacklist organizations before, and because of it, there could be more misclassification. Now, what the recommendation system does is it tries to find IP addresses that are similar to these misclassifications, and also tries to find blacklists that list such IP addresses. The final stage of Black is a selective expansion phase where it selectively identifies some of the IP addresses and expands them into /24 prefix. Here, it does so in 2 checks. In the first check, Black checks if there are any other IP addresses that are listed in the same /24 prefix as are the known misclassifications. In this example, there are no IP addresses that are co-located in the same /24 prefix, so all the IP addresses pass check 1. In check 2, Black checks if there are IP addresses co-located in the same /24 prefix as the likely misclassifications recommended by our recommendation system. In this example, IP3 is in the same /24 prefix as IP1, therefore it fails check 2. Black then expands all the IP addresses into /24 prefix that has passed both check 1 and check 2, and leaves the IP addresses that has failed either one of the checks. Now, I'll quickly touch upon our data sets which we use to evaluate Black. So like I mentioned before, we used about 157 blacklists for different attack types, monitored from in 2016 to 2017, and we collected about 176 million IP addresses during this period. Now, in order to evaluate the performance of Black, we had to curate 3 different network traces across different types of attacks. The first one is the email dataset, where we try to apply Black for capturing spam and ham emails, where we want to maximize the spam email collection and try to minimize the number of ham emails also falsely misclassified. The other 2 datasets involve DDoS attacks in a university and a B-root DNS server. In my talk, I'm just going to talk about the email dataset, but you could find the details for the other 2 datasets in the paper. So the email dataset was collected during the month of June in 2016. We used the first 7 days as a training dataset to curate the misclassification blacklist used by the recommendation system. We then used the next 7 days to have a validation dataset to curate the threshold, which is again used by the recommendation system to prune out the misclassification. Finally, we used the next 2 weeks to see the performance of Black. So we see that for the legitimate source, we conducted an IRB study where we recruited about 35 volunteers who gave access to their Gmail account, and we extracted only the source IP addresses of legitimate emails. We made sure that we did not collect any identifiable information from our volunteers. For the attack dataset, we used Mailnator, which is a publicly available inbox, which is known to get a lot of spam emails. So we pulled all the emails, ran it through Spam Assassin, and extracted only the source IP of malicious emails, and that formed our attack dataset. So on to evaluation. We compared Black with 3 approaches. The first approach is known as the best blacklist, where among the 157 blacklists, we choose the best performing blacklist. Note that this is a very hypothetical scenario, because the network operator would not know which blacklist is going to perform the best. The second is a historical blacklist, where we combine all the 157 blacklists and all the IP addresses that were ever listed in them. And third is Presta, where we run the Presta algorithm, which uses spatial and temporal properties of blacklists to curate a blacklist for a particular network. We compare the performance of blacklists in terms of specificity and recall, where specificity is a percentage of legitimate addresses that were not false positives, and recall is a total number of attacks that were detected. So a good blacklist will have very high specificity and high recall. So First, we observed that for best blacklist, it has very high specificity, close to 100%, but recall is very low, less than 4%. Historical blacklists improved the recall to about 18%, but the specificity drops to about 88%. BLAG, on the other hand, has 65% spam email detection, but it also keeps the specificity high of about 95%. We then tuned Presta to have the same recall as that of BLAG and compared their specificity. Presta has a specificity of about 82%, while compared to 95% of BLAG. The main reason is that Presta works upon blacklists which are paid for, and they're known to have less misclassifications. However, we work with publicly available blacklists that have many more misclassifications. So we did a bunch of other evaluations, and on other two data sets, we ran a bunch of micro benchmarks to test the parameters. You can find the details in the paper. Finally, all the monitored blacklists are constantly being collected, and you can find the data sets and the scripts to run BLAG. So in summary, blacklists have poor attack detection, and if you were to combine blacklists of different attack types, you could possibly improve the attack detection. However, there may be many misclassifications. So we present BLAG, which monitors about 157 blacklists, combines them together, and then uses a recommendation system to prune out the misclassification. BLAG has better performance than competing approaches. This is the end of my talk. I'm just going to leave this over here so that you can take a picture, I guess, and then I'm up for questions. Thank you.
Victor Bouchard, Leuven. How easy is it to collect the list of legitimate IP addresses or IP blocks?
Oh yeah, that's a good question. So we found that networks usually have existing systems in place, such as intrusion detection systems. So what we propose is that for a sample duration of time, say a week, they could actually monitor the legitimate traffic which the network usually sees. So all the traffic which doesn't go, gets blocked by the intrusion detection system could be potentially used as the IP addresses for the misclassification blacklist.
And what would the effect be of a illegitimate IP address getting into this list of legitimate IP addresses?
Yeah, that's a good point. So since we use only IP addresses as an identifier, here there could be potential false positives. So we have actually discussed this in a paper where we try to vary the total number of legitimate addresses available to BLAG, and the system the performance decreases because if we show only few legitimate addresses, then the detection is not enough for the recommendation system to capture similar IP addresses.
Okay, thank you.
Yep.
Hello.
Hi.
What was the intersection between the blacklists that you drew upon?
So intersection between
or
what and
how
what?
much overlap was there between these 150 blacklists?
Oh yeah. So there were many blacklists which listed only a few IP addresses because they were potentially maintained by only individual maintainers who saw attack in their network. So it's if we discuss this in the paper, we see that about the top 10 blacklists contribute about 75% of all the IP addresses that was seen. Yeah.
Speaker again.
Thank you.